Hello students, this class we are going to discuss some more applications of potential due to charged bodies. In that first one we are going to discuss today linear charged wire of infinite length. Now consider one of the wire of infinite length which carries the charge. So this is the one of the wire we chosen of infinite length. So which carries the charge. The charge is which is given on this one distributed linearly. So this is linear charge distributed wire. So here the charge distribution is according to the concept is this is linear charge distribution, that is lambda. So you know that total charge of the wire is Q if you say, total length of the wire is L if you say, lambda is equal to Q by L. That is nothing but total charge on the wire is equal to lambda into L. Now what we are calculating? We are calculating the potential at a point due to this charged wire at a point of distance R. So here I chosen one of the point. So you can see here, this is the point we chosen here, this is the point P. At this point, we are finding the potential due to this infinite length charged wire. The distance of the point is we taken at a distance of you can take it as some x we can see. Now to calculate this one, first potential versus electric field relation, we know that because according to the relation between potential and electric field, V is equal to minus E into R is the formula. So in the case of small portion, that means due to elementary portion of this charged wire, so elementary potential difference equal to minus, that is E into elementary distance of elementary position of that one, that is you can take it as minus E into dr is the formula. Now here what is the electric field due to this infinite charged wire? So electric field due to a infinite charged wire already we learned in the previous class. That formula is equal to what I can write, that is lambda by 2 pi epsilon naught into R is the formula for this electric field due to infinite length wire at any point. So now apply this formula there. What is the lambda? That is linear charge density. 2 pi epsilon naught is constant. R is the distance of the point. Here in the case of this one, R is not the distance. In this diagram we have chosen the distance is x. So there is lambda by 2 pi epsilon naught x. So here if it is x means automatically the change in potential also in terms of according to distance we can write as minus E into dx we can write. Now apply the integration both the sides. Now we have to apply the limits here. So integral dv is equal to v is the formula minus into electric field. So what is the electric field at a distance of x point, because we chosen the point at a distance of x. So at a distance of x, electric field is equal to, that is lambda by 2 pi epsilon naught into x into dx is the formula for this. Now in this case take the constant outside, minus lambda is outside, 2 pi epsilon naught is also outside, these are all constants, and this is integral dx by x is the formula for this. Now we have to integrate this one. If we have a limit between the 2 points, that means suppose if I choose in the point here, one point here, and if I choose in the another point here, that is this point I am calling as A point, this point I am calling as B point, then you can integrate this one. The position of this A point, if you take as, that is sorry, you take as XA. The position of this A point, you take it as XA point if it is. The position of the B point, if you say as XB point, then you can apply the limits for this one from XA to XB. That means A point to B point. Now I am not doing any limits here. We are choosing only single point at a distance of x. So directly you can integrate this one. So according to the integration, so what we are going to get, V is equal to, that is lambda by 2 pi epsilon naught into integral dx by x is equal to, that is log x is the formula for this. So this is the formula of potential due to a linearly charged wire of infinite length lambda by 2 pi epsilon naught, that is ln x. Suppose if you apply the limits to this one, suppose what is the limits function, V is equal to, that is nothing but minus lambda by, minus also will be there here, minus lambda by, that is 2 pi epsilon naught into, that is integral dx by x. If you apply the limits, that is xa to xb, if you apply the limits, so in this case the formula will becomes, that is equal to lambda by 2 pi epsilon naught, that is minus integral, that is anyway log x, that is log x. Lower limit is you can apply, that is xa2, that is upper limit is xp. If you apply that one, v is equal to, that is nothing but, if you take in this one log, that is xb minus log xa. Log a minus log b is equal to log a by b is the formula, that is nothing but minus lambda into 2 pi epsilon naught. What you do is take the minus inside. If you take a minus inside, then it becomes log xa minus, that is log xb. That means ln xa minus ln xb. That means we can write this is lambda by 2 pi epsilon naught, that is ln log a minus log b is equal to log a by b. That means I can write this is a, this is b, means that is xa by xb is the formula. So potential due to this infinitely charged wire at a point of distance x equal to lambda by 2 pi epsilon naught ln xa by xb is the formula for this. Now we will discuss the potential due to dipole. So already in the previous class we know about what is dipole concept. Dipole is nothing but two charges, two similar charges separated by small distance called as dipole. Here I am taking the two charges here. One is plus q, second one is minus q. Both are separated by small distance. You take the q value is equal to small q like minus q plus q like, if you taken separated by distance. The separation distance between these two, if it is small distance, that is 2l from the center of the dipole. This is called center of the dipole. Now this, due to this dipole, what is the potential at any point due to this dipole, we are going to discuss now. Here there are two concepts are there. That is, if you taken this line, this is the line which you are taking, which is passing through the axis of the dipole. This line is called as axial line. Already you know that this is axial line. Now the line which you taken normal to the center of the dipole, this is called equatorial line. Now we are finding the potential at a point P, that is along axial line, that is nothing but VA, and also we are going to find next potential due to this one at any point along equatorial line, that is VT. So to find the potential at a point along axial line, so first consider two charges. One is minus q, second one is plus q I taken here. Now this is the line joining between these two charges called as axis of the dipole, and this is the center of the dipole, I can say, that is O. From the center, the positive is separated by distance of L, the negative charge also separated by distance of L. Now I choose a point outside of this charge at a distance here. The distance of this point is from the center, always you have to calculate from the center, you have to calculate always from the center. The distance of the point is at a distance of r, if you say. Now a distance of r, the point is located. Now I want to calculate that potential at this point. That point is located along axial line, that's why that is called potential due to charge, okay, along axial line, that is VA. Now to calculate this one, already you know that dipole contains a dipole moment that will be always from negative to positive, that is P. This is the direction of the dipole moment, and electric field also exists at that point in the same direction of the dipole in the case of axial line. So electric field exists in this direction. Next, the positive charge. There is a potential due to positive charge at that point. Now what is the distance of the q plus q? The plus q is the distance from the center to point is r, and the charge is a distance of, from the diagram I can say here, r minus L is the distance of the point. Now if you come across a case of negative charge, what is the distance of the negative charge? The distance of the negative charge from here to here is r, from here to here is L. Total distance becomes r plus L, is the total distance of the negative charge from the point. So two charges are a distance of r plus L, r minus L from the point. So due to both the charges, the total potential at that point is equal to, potential is scalar quantity, so potential is equal to potential due to positive charge plus potential due to negative charge at that point you have to take. So now what is the potential due to positive charge? Potential due to positive charge is equal to nothing but, formula is 1 by 4 pi epsilon naught, q by r is the formula, so that I am writing as k into charge is, that is nothing but q plus q by distance. What is the distance of that one? R minus L is the distance of that one. This is potential due to this positive charge at this point. Now what is the potential due to negative charge? That is equal to k into, that is q, but minus you have to take because negative charge, by distance of that one is r plus L, you have to take according to formula. So apply this one in this. So net potential at that point is equal to what is common? K into Q is common in both the cases. If you take in common that one, you are going to get 1 by R minus L minus 1 by R plus L here. If you take an LCM and if you calculate, this is V net is equal to, you are going to get K into Q into, if you take an LCM of this one, that is R minus L into R plus L, you are going to get, that is nothing but R plus L minus R plus L, you are going to get by, this is A plus B into A minus B formula, I convert directly as R square minus L square, you are going to get in the denominator. So here plus R minus R get cancelled. So this equation I can write in terms of as, that is K into Q into L plus L, that becomes 2L by, that is R square plus minus L square here. So according to the dipole moment, what is the dipole moment? That is P. The P dipole moment we can express, we can define, it is the product of charge into length of the dipole, that is Q into 2L. So that I can replace this Q into 2L with the P, so that potential at a net potential at that point, that is called axial potential, is equal to, that is K into P by, that you are going to get R square minus L square here. This is one equation. In the case, suppose if L is much, that means if the length of the dipole is much smaller than compared to the distance of the point, that is R. In this case, I can neglect the length of the dipole. If we neglect the length of the dipole, what the equation becomes? The axial field, the axial potential is equal to nothing but K into P by, that is you are going to get L value becomes 0 means R square here. Potential at a point is inversely to distance due to a single charge, but potential due to dipole is inversely to square of the distance here. This is important to note, that the potential is due to a charge is inversely to distance, the potential due to dipole is inversely to square of the distance. This is one of the expression for potential due to a dipole. At what line? Along axial line. Now we are going to discuss next one, along equatorial line. Now we will discuss the potential due to dipole along the equatorial line for the dipole. So consider one of the dipole here, I take a negative charge, positive charge here. Now I choose an equatorial line. This is the point I chosen here at along equatorial line, which is a distance of R from the center of the dipole. Now with respect to the charge minus Q, the distance of the point is under root of R square plus L square according to Pythagoras theorem we can apply. So what is the potential at that point due to this dipole? If you want to calculate, we have two charges are there. Now with respect to the charge, both the charges, that means negative charge is at a distance from the point P is R square plus L square. Similarly positive charge also at a distance of same, that is under root of R square plus L square only from the, using that right angle triangle structure. So there are two potentials are exist at that point. So net potential is equal to nothing but we can write as potential due to positive charge plus potential due to negative charge. Now what is the potential due to positive charge? That is 1 by 4 pi epsilon naught, I can write as K into charge. What is the charge? That is first one I am taking positive charge, that is Q, by distance of that point positive charge from the point P. What is the distance of that one? That is nothing but under root of R square plus L square is the distance of this, and plus addition of potential due to negative charge. So here the charge is negative, that's why in this case we are going to write minus K into, the charge is negative charge, that's why plus into minus becomes minus, and under root of this becomes R square plus L square. If you observe this equation, V net is equal to, so both the values K, K, Q, Q, so both are similar, but one is plus, one is minus, the net value will become equal to 0. So there are two charges are present and there is a line, okay, passing through the center of the dipole. In this case potential is becoming 0. Potential becoming 0 means this line is called as equipotential surface. Equipotential surface. What is the meaning of equipotential surface? Where the potential difference will be becomes equal to 0. Here also the potential difference between these two, positive and negative charge, will become 0, means that is called equipotential line. So at any point on this equatorial line, the potential will be is equal to 0 due to dipole. So that means what is the work done along this line? Potential is 0 means nothing but work done is equal to, along that line is equal to, also becomes equal to 0. The work done along that line is equal to 0. That means if you take any test charge here, what happens automatically? No need to do any work. So automatically it will be move towards this line along the equatorial line without doing any work, extra work. That's why along the equipotential surface, potential is 0. Automatically work done to move the charge along that line also equal to 0. So this is the concept of potential due to dipole along equatorial line. So what is the conclusion? Along axial line there is a potential, along equatorial line what is the potential? That is equal to 0.